Hi, I'm Yanjie. I will be presenting our work, Resource-Guided Configuration Space Reduction for Deep Learning Models. This is a joint work with Yonghao from Microsoft Research, Hongyu from Newcastle, and Haoxiang Mao from Microsoft Research. Deep learning models provide many configuration options for users to tune, such as hyperparameter and neural architecture. This model has several operators such as convolution, average pooling. Each stack represents a feed-forward structure called cells. For example, the default model's cell contains multiple convolution operators with 3 times 3 filter sets, in addition to input and output operators. When hyperparameter tuning, the filter size of convolution operators is adjusted, shown in the red cell. For neural architecture search, the connection between operators of the model is changed for the new architecture. According to current trends, the configuration space becomes huge. For example, the NASBench 101 benchmark has lots of model configurations in total, which cost huge training hours on one TPU. Resources for training or inference, such as available GPU memory, computing power of devices, execution time, are limited and precious. Resources impose computational constraints on model configurations. For example, model weight size should be smaller than allotted binary size. GPU memory consumption should be smaller than device memory capacity. Non-conforming model configurations lead to many failed jobs or inappropriate models. AutoML has been widely adopted to automate model training by systematically exploring the configuration space. Each arrow represents searching a model with specific configuration until find the best model. However, resources required by a model configuration often remain unknown to user before the job execution. Non-conforming model configurations could lead to many failed AutoML trials. For example, the model weight size is out of range, out of GPU memory, number of floating point operations is too large, model inference time is too long. However, since the GPU memory consumed by a DR model is often unknown before the training or inference job starts running, an improper model configuration can cause such a job to run out of the limited GPU memory and fail. As shown in figure, if a PyTorch ResNet 50 training job with a batch size of 256 is scheduled on the P40 GPU, it will execute normally and consume 22 GB memory. But when it is scheduled on the P100 GPU, it will trigger an OOM exception because P100 has only 16 GB in total. Other hundreds of AutoML jobs with the same batch size could also experience OOM and crash. We summarized some of the benefits of resource-guided AutoML. It could help AutoML tools efficiently prune the configuration space ahead of time, exclude unsatisfiable model configurations, and save resources to try more. It can speed up search to achieve even better learning performance. We propose a resource-guided configuration space reduction approach, which is called DnnSAT, based on the following observations. We formulate such a resource-guided space reduction problem as a constraint satisfaction problem. Include a unified analytic cost model to calculate resource usage and construct common constraints. For example, the model weight size. We utilize the Microsoft Z3 SMT solver to obtain the satisfiable model configurations before job execution. Accelerate the constraint solving by parallel solving, tiny space, and interval filtering. This figure shows the workflow of DnnSAT. First, it will pass and reconstruct an input model into the corresponding computation graph. Next, it will traverse the computation graph with a predefined operator schedule to automatically generate constraint specifications in SMT lib for later solving. It contains two working modes. The first figure shows a simple TensorFlow training program using the Keras API, which sets up a sequential model with the framework built-in com2d, average put2d, flatten, and dense operators. The filter size, kernel size, and the number of units are hyperparameters, which are parameters to control the training process. The second figure shows the setting of the training program supported by the AutoML tool NI with HPO. The code defines the possible values of tunable hyperparameters. This configuration space contains 288 model configurations. I will illustrate the mechanism of DnnSAT by a sample constraint on model weight size. This figure demonstrates the corresponding computation graph for the model in previous program. With the execution of each operator, DnnSAT will generate weight size needed by the operator. First, DnnSAT will set the hyperparameters and their domain for each operator. Next, DnnSAT traverses the computation graph from com2d to dense one after another. For each operator, we prepare SMT-lib templates via these three APIs for the resource cost functions. Then DnnSAT will calculate each operator's weight size. The total model weight size is equal to the sum of the weight size of both com2d and dense. The line 25 to 26 shows the weight size calculation. Finally, DnnSAT asserts that the results must fall between the lower and upper bounds, and so the satisfied configurations by line 29. I will introduce our experimental design to prove the effectiveness of DnnSAT. We evaluate DnnSAT over popular AutoML benchmarks and methods, and we also evaluate DnnSAT over real-world models. We use the speedup and space ratio to evaluate the effectiveness. For the speedup, t-base is the estimated time of a baseline reaching the lowest test measurement, and t-DnnSAT is the time of a DnnSAT guided method reaching the same or lower test measurement. For space ratio, delta and delta DnnSAT are the original and reduced configuration spaces. A smaller SR means a stronger reduction effect. In this section, we consider the model weight size constraint and evaluate the effectiveness of DnnSAT on benchmarks. We perform two sets of experiments, baseline and DnnSAT guided experiments over four representative AutoML methods. We then measure the speedup achieved by DnnSAT over each baseline method on each benchmark. The speedup is calculated as t-base divided by t-DnnSAT. Figure 6 demonstrates the test measurement curves of HPO bench. Figure 7 demonstrates the test measurement curves of NAS bench 101. The x-axis is the work clock time, and the y-axis denotes the test measurement value. Overall, DnnSAT achieves a speedup of 1.19 times to 3.95 times on HPO bench, and achieves a speedup of 1.19 times to 1.52 times on NAS bench 101. In this section, we evaluate the reduction effectiveness of DnnSAT on real-world DR models. We choose two representative models as our experimental subjects, namely VG16 and sequence-to-sequence. A smaller space ratio indicates that better reduction effectiveness. We apply all the four discussed constraints separately and collectively to both DR models. Each constraint is set with several upper bounds. For example, the space ratio of VG16 under the GPU memory consumption constraints ranges from 42.1% to 84.3%. Tighter bounds or a combination of multiple constraints will lead to a more significant reduction. The results can also give hints to developers and help them choose optimal settings of new architectures, hyperparameters, and computational resources. Thank you very much. Let's enter the question and answer section.
Well, hello, everyone. Welcome to the session on configuration of software systems optimization. My name is Sergio Segura. I will be the chair of this session. We have three very interesting papers in the session, one from the technical track and two journal first papers. By now, you will probably be familiar with the procedure for Q&A, right? You must write questions during the talk in the chat, and then I will ask those questions verbally to the speaker. Remember that at the end of each Q&A, you will see a pop-up window with a link for going to the discussion room, a specific discussion room for that paper. If you want to continue discussing with the author, please wait for it and press the link. This is the question and answer slot for the paper, Resource Guided Configuration Space Reduction for Deep Learning Models. And we have here with us, we have the pleasure to count with Janjie. Okay, so it's time for questions. Remember that you can write those in the chat. Don't be shy. Fire away. Okay.
Thanks, Sergio's introduction.
While we have questions, I don't see any in the chat. I have a few, Janji and myself. Okay, I will start with the questions.
Okay, thanks.
Yes, well, your paper is based on using, your paper use constraint programming, right?
Yes.
You use constraint satisfaction. In my experience with constraint satisfaction problems is that they often have inconsistencies. Very often they have errors, you know?
Yes.
For example, variables that can never be selected because of contradictory constraints. So my question is, how frequent do you think that inconsistencies can appear in your domain, and whether your approach, your tool, can detect those inconsistencies?
Okay. Oh, for my understanding for the questions, I think it is similar to the errors we once made, because the resource estimation, we have not formally analyzed the false estimation rate for the memory and the time constraints. We encountered a small number of failed jobs for the experiments, less than 10%, and no valid configurations were discarded. For other constraints, like the width size and flops, we didn't encounter the failed jobs. We will include this discussion. Because yes.
Okay, I see. Well, the approach, well, your tool can work in two modes, right? The interactive mode and the pruning mode. In the interactive mode, you basically check the validity of each individual configuration.
Yes.
Typically, constraint solvers support explanations. You know, they can explain why a configuration, a solution is valid or not. Well, why it's not valid. My question is, have you considered using those kind of operations for providing feedback to the users about why certain configurations are being ruled out? You know, why they are being discarded?
Okay. This is a very deep question. I think this is for the interactive mode. It is easy for us to show that because we also summarize the estimation cost for the resources such as the memory consumption, the flops, and the width size, so user can have the explanation for this because they know the real resource why out of the constraints. For the search space pruning, like the pruning mode, we will also try to include the SMT, the unset call functionality, because we could show the out of constraint the constraints, so that can give users some explanation. Also, if user need more debugging infos, we could make the pruning mode as the interactive mode to show more details debugging informations. So if user need speed, they could use unset call mode. Yes.
Okay, I see. in the planning mode, you calculate all the configurations, right?
Yes.
And that's really time consuming, right? You mentioned here that it takes 5.5 hours for 24,000 configurations. That's also my experience. It's really time consuming. My
Yes.
question here is, have you considered calculating the number of configurations beforehand for giving the user an estimation of the computational cost?
Yes, for the time-consuming problem, we try to include some system optimizations. For example, parallel solving, like we thread execution or the distributed execution. And we also found that if we could split the search space to tiny space, so the solver will not include more constraints, it can be more faster. And we also found some tricks like the interval filtering, because some like a batch size, the batch size is the training samples number. If the batch size out of one resource constraint, maybe the larger one will also out of that constraint, for example. So we also can filter more search space. After including these optimizations, we found that we could provide the user a reasonable solving time.
Okay, thank you very much, Janji.
Thank you.
Well, I do not have any more questions. Anyone in the audience would like to participate? We still have 3 more minutes. Well, just in case, Janji, I suggest that you stay here for 3 more minutes, okay? Just in case someone want to participate, want to ask a question. Remember that if you want to go to a specific discussion room for this paper, you will see a pop-up at the end of this slot in about 1.5 minutes with a link. Please click on the link if you want to go to that discussion room with Janji in order to continue discussing his very interesting paper. So that's it. Janji, thank you so much for your presentation and for your answers. And good luck with your research. See you all in the next Q&A. Bye.
Bye. Thank you. Thank you.